Yeah, hi everyone, this is Bhimar Kumar Samal. So we'll be streaming another video and we'll be studying about medical science. Study with me, guys. We're gonna just place on a laptop and do your own study so that you'll feel that someone is guiding you. So primary active transport move ion across the membrane, creating difference in potential, difference in charge across the membrane. And due to the difference and secondary active transport exercise the movement of material due to the electrical gradient established by the primary active transport that does not require ATP. Concentration of sodium is 10 times higher than the outside. This concentration. talking about you, idiot. Why your name is also raised? The electric potential arises from both from ion bonds and from the flow of ions through channels. Perfect.
Across a cell membrane. Most cells have a negative transmembrane potential. Because membrane potential is defined relative to the exterior of the cell, the negative sign means the cell has more negative charges on the inside. There are two basic rules governing the movement of ions. They move from higher to lower concentration, just like any other molecules. Being charge-bearing particles, ions also move away from like charges and toward opposite charges. In the case of the cell membrane, there is a third factor that controls ion movement: the permeability of the membrane to different ions. Permeability is achieved by opening or closing passageways for specific ions, called ion channels. Permeability can change when the cell adopts a different physiological state. Consider this example. Two solutions of different concentrations of sodium chloride are separated by a membrane. If the membrane is equally permeable to both sodium and chloride, both ions will diffuse from higher to lower concentration, and the two solutions will eventually have the same concentration. Note that the electric charges remain the same on both sides and membrane potential is zero. Now let's assume that the membrane is permeable only to the positively charged sodium ions. letting them flow down the concentration gradient while blocking the negatively charged chloride ions from crossing to the other side.
Ion flow from higher potential to lower potential, okay. And it only allow positive charge. Sodium will move, okay. Okay.
This would result in one solution becoming increasingly positive and the other increasingly negative. Since opposite charges attract and like charges repel, positive sodium
But look at this.
increasingly positive.
Na plus Cl minus. Minus 3. Oh, this is dominated by 3 chlorine and this is dominated by 3 sodium. Acha, and sodium charge is more. Acha, got it.
While blocking the negatively charged chloride ions from crossing to the other side. This would result in one solution becoming increasingly positive and the other increasingly negative. Since opposite charges attract and like charges repel, positive sodium ions are now under influence of two forces. Diffusion force drives them in one direction, while electrostatic force drives them in the opposite direction. The equilibrium is reached when these two forces completely counteract, at which point the net movement of sodium is zero. Note that there is now a difference of electric charge across the membrane. There is also a concentration gradient of sodium. The two gradients are driving sodium in opposite directions with the exact same force. The voltage established at this point is called the equilibrium potential for sodium. It's the
So
voltage
it's saying that if the net charge, if the charge is not flowing, that doesn't mean the charge concentration is actually equal. That mean then the diffusion force and the electrostatic force is getting same. Okay, yes, flow नहीं हो रहा है मतलब अभी same है. Okay.
Required to maintain sodium in opposite directions with the exact same force. The voltage established at this point is called the equilibrium potential for sodium. It's the voltage required to maintain this particular concentration gradient and can be calculated as a function thereof. A typical resting neuron maintains unequal distributions of different ions across the cell membrane. These gradients are used to calculate their equilibrium potentials. The positive and negative signs represent the direction of membrane potential. Because sodium gradient is directed into the cell, its equilibrium potential must be positive to drive sodium out. Potassium has the reverse concentration gradient, hence negative equilibrium potential. Chloride has the same inward concentration direction as sodium, but because it's a negative charge, it requires a negative environment inside the cell to push it out. The resting membrane potential of a neuron is about negative 70 millivolts. Notice that only chloride has the equilibrium.
Okay, I'm really sorry for disturbing what I really have to do. So everything is done now. So let's stop. Something.
Equilibrium potential near this value. This means chloride is in equilibrium in resting neuron.
Okay, guys. Sorry for taking pause. Good night, guys. We'll be back. Time to brush, guys. You all know. नहाने का मूड नहीं कर रहा है आज नहीं नहाऊंगा ओह back to come on.
while sodium and potassium are not.
So yeah, this is the value that a sodium. Okay, wait. What? Potassium is positive charge, right? How can this be possible? How is this possible? Sodium is positive, I get it, 60 millivolt. Chlorine is negative, minus 20 volt. Okay, get it. How can potassium is negative? Why do we say K plus then? That plus in K is not the same thing as minus 80 kilopotential. K plus potassium ion has a positive ion charge. Yes. What do you mean by positive? Your positive is minus 90. Okay, sodium. Okay. It means the inside of the cell must be about 90 millivolt more negative than the outside. Achha. To stop potassium from moving. Oh God. Oh, I cannot get it, man. Step 1. There are a lot of potassium inside the cell. Imagine. Are you getting it? I couldn't get nothing, bro. But I like breeze. इतना भी नहीं और मेरे ऊपर नहीं किताबों के ऊपर समझ में तो कुछ नहीं आ रहा है Oh, oh, ho, ho, ho. Acha, minus 90 millivolt is the potential at which if you keep the cell membrane at this potential, the potential potassium will not move out. Because at that point, concentration gradient force will be equal to the electric gradient. Okay. So naturally, as a cell, potassium is remain inside, and the charge of sodium is 10 times more outside the cell. Oh, that is why. That is why the okay. Taking time a lot of time. Taking a lot of time. कल हो ना हो la 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 la. Now you are noise free. Yeah. Wow. We're live. So we're live. We're nothing now. Okay. That's awesome. What's up with that? Ha, did you get it, bro? Full क्यों नहीं हो रहा? अच्छा. Oh God, oh God. Oh, I cannot get it. You'll never get it, man. Fuck you. You'll never get it. Watching live myself in a live video, it's a great experience. Yeah, I cannot do that. I need to break. Okay, bye guys.